let's begin.
So, like I said, we're going to do example 4. I believe last time we did 1 and 2. It's kind of 1 and 2. So, from the handout, okay. Plane carrying food and water to a resort island can carry a maximum of 30,000 pounds, and it is limited in space to carry no more than 535 feet. Each container of water weighs 60 pounds and takes up 1 cubic foot each container. Okay, so they're telling us a bunch of stuff. Let's actually collect this data here. Let's talk about food. This is called X in the problem. And let's talk about water. It's called Y, number of water containers. Let's talk about the total. Let's talk about, it mentioned also, it mentions weight. It mentions the amount of space it takes up. And it's also going to mention the price. Okay. So I have a plane carrying food and water to a resort island. The maximum capacity is 30,000. Maximum weight capacity is 30,000 pounds. And the space is 525 cubic feet. Okay, each container of water weighs 60 pounds and takes up 1 cubic foot. Or actually closer to 62 or whatever. Each container of food is 150 pounds and takes up 5 cubic feet. Hotels on the island will buy each item of food for $16, so the price of that is $16 per pound. And the water for $5 per pound. What is the optimal number of containers of each item that will maximize the revenue generated by the plane? So basically we want the max here. And what is the maximum revenue? Let X equals the number of food containers and Y equals the number of water containers. Okay, so we have this situation. A plane is carrying food and water to some island, and we don't really care how much food or water these people have. We just care about making the most money we can. Okay, so if we just have to give them food and no water, that's what we're doing, because that's we only care about the maximum revenue there. So our objective. We already have the variables, so we don't need to define them. But we do have an objective. The objective is to maximize revenue. What is the revenue here? Yeah? 16x plus 5y. This is the amount of dollars I make per pound of food. That's the amount of dollars I make per pound of water. So this is the total amount of money I make, and that is our objective function. We want to maximize. Now, what are the constraints?
$150x plus 60y must be less than or equal to 40,000.
Okay. Now the total amount of weight that the products have must be less than or equal to 30,000. And so I have a constraint on the weight. I can't carry an infinite amount of food and water. because that's what we would do. So there's a restriction here. Another restriction is, of course, space. The plane cannot be packed with an infinite volume, so the volume that we are going to have is going to come from 5x plus 1y. And that must be less than 525, because we can't have any more space than that. Now, automatically, this is x is greater than or equal to 0 and y is greater than or equal to 0. And in fact, only integer solutions would make sense to us here. Well, no, not even just integer solutions, just anything that's 0 or bigger. In theory, you could bring half a pound or something, I would say. So that is the situation. It is a linear programming problem. So what do we do now? How do we actually solve the linear programming problem? Yeah. You first sketch the feasible region, and you sketch the constraints. You don't sketch this guy. These guys are what contribute to your sketch. So here's the x, here's the y, and of course x equals 0 is here, y equals 0 is there. What does this guy look like? Okay, so you're going to plug in x equals 0, and y is that divided by, y is going to be 30,000 divided by 60, which is it's 500.
Yeah.
And then the x, plug in y equals 0, solve for x, what do we get? 200. 200. So connect these. It should be a straight line. So this is our weight equation. Our weight equation being plotted. Now if we plot volume, the y equals 525. And the x would be 525 divided by 5, which is going to be what? 105. So that's going to go here, go there. It's the volume equation, and it hits here at 105. And that's all we have. Now, where would our feasible region be? It's below both of the lines at the same time, but to the right of this one and above that one, that gives us this region right here. And of course, based on the theorem that we had last week, we know that what's important to us is going to actually be the corner points of the feasible region. Now, three of them are easy. This is 0, 0. This is 105, comma 0. This is a 0, comma 500. And this one is, well, let's figure it out. Pretty much set these two, solve the system of equations. Let's find what that point is. So we have 5x plus y equals 525. And for the other one, well, I can divide through by 10. Then divide through again by 5. 5 into this would go 3 times. 5 into, divide by 3. 3 into this goes 5 times. 3 into this goes 2 times. And 3 into this is 1,000. So this will look like 5x plus 2y equals 1,000. Call this equation 1, that equation 2. Let's take 2 minus 1. And so we'd have y equals, what is this here? 475. And our x would equal, well, 525 minus 475 all over 5. 10. That's 10. So this guy here is 10, comma 475. So these are our options. I mean, it's pretty much obvious, like 0, 0 is not going to be what we want. That's like, you stay home. This one over here, it's going to be like, we are going to give them 500 pounds of water and no food, or we're going to give them 105 pounds of food but no water. And yeah, that's what we're going to do if that's the best situation. So let's hope for their sake that the solution is going to be that one. But at the end of the day, got kids to, you gotta do what you gotta do. So the next step is to actually test all the values. So your f was 16x plus 5y. And we have, I mean, as a courtesy, let's put that in there, but we know that's not going to be what we want. We also have 0, 500. We also have 105, 0. And we have 10, 475. So what we're going to do is we're going to plug those into the equation. So we have 0 plus 5 times 500, or is that 2500? Or we can have 16 times 105 plus 0, which is what? 1600? 1680. Or we can have 16 times 10 plus 5 times 475. 2,500 what? Oh, they're so lucky. Barely made it. Fine. We'll give them both food and water. We'll make an extra $35 by doing that. And yeah, so the max revenue that this plane can carry is going to be $253.5 per trip. And this occurs at 10 pounds of food and 475 pounds of water. So that's our answer right here. And that's linear programming, kind of in a nutshell. Like I said, on the test, unlike the midterm, problem's going to be like this level of difficulty, maybe slightly higher, but not much. So once you can get through this, you should be okay. So the steps are define your variables, of course, set up your objective and constraint equations. You're going to sketch your constraints to find your feasible region. You are then going to find all the corner points of the feasible region because that's where your solution is going to show up. Sometimes to find the location of a corner point, you need to solve a system of equations, maybe several, and then you test all the values. You pick the maximum or the minimum based on what you're actually looking for, and yeah, you're done. Any questions on the process? So that's kind of all I wanted to do. I know we didn't do problem 2, but I'd like you to try that on your own. Maybe next time I'll tell you the answer, but for now just try that on your own because there's a little trick in that one which I want to see if you guys can catch on to. But yeah, that's kind of it. That's it for linear programming. That's the geometric approach. You can solve some very useful kind of problems that way. Now we're going to move on to something actually a little bit different, and because it's a new topic, we're going to start very slow. We're going to start talking about set theory. Set theory, most people go, oh, we're going to draw Venn diagrams and stuff, yay! When I hear the word set theory, I kind of go back to a very dark place, because I took a graduate course in set theory once when I was an undergrad. Yeah, I still have nightmares about it. It was one of the pivotal moments in my life, I would say. It's one of the things, you know, sometimes things happen in your life that makes you who you are. Set theory was one of those things. Yeah. It starts out pretty easy, but eventually you go far enough, it gets really hard and really crazy. And yeah, the worst grade I've ever gotten was in set theory. Better not. We're not going to go that far. We are going to keep things relatively simple. We just need to understand set theory just enough. We're going to do some things where we deal with sets directly, but the main goal for me and for us is we want to learn about sets just enough to actually be good at probability, because we're going to do probability. It's a very important topic, and you deal a lot with sets. In fact, to solve probability problems, you need to figure out the certain sets and sets of sets. And usually if people get a probability problem wrong, it's because they're thinking of the wrong set while they're doing something. So we want to learn set theory very well, so that we can actually start to think properly and logically when doing probability. So let's start with a definition. What is a set? You know what's a set? Simply a collection of objects. We call this a set. Is an unordered collection of objects. The objects are called the members or elements of the set. Writing down the members, here's one more important criteria for a set. Repetition is not allowed. Or rather, repetition is ignored. You have an unordered collection of objects where you don't want to repeat anything. We call this a set. There are many things that can be considered sets. Right? So if I have an Airbnb and I'm talking about the amenities of my Airbnb, I can actually list them in a set. I can say, hey, we got Wi-Fi, we got space heaters, we have AC if you want AC. I can list all the amenities of the Airbnb. Now, one, the order of such a list doesn't actually matter. There's no inherent order. It's not like Wi-Fi always comes first and then this comes second. No, it depends on the person. So there's no inherent order. And also, repeats would be ignored. So I can't be like, oh, we have Wi-Fi. We have Wi-Fi. You're just going to say you said the same thing twice. You're not going to fool me. That's one amenity. You just said it twice, right? So sets is talking about the kind of collections that we do not have repetitions, we do not have order. None of this is inherent in a set. It's just an unordered, non-repeating collection of objects. We call these objects the members of the set. Notation. Common notation. It's called the roster method. This is where you list the guys in the set and you list them inside of squiggly brackets, like that. So I can have a set A, B, C, D, E, And by the way, we can give sets names, usually uppercase letters. So we can name sets. And this method of naming them is called the roster notation. That's when you want to actually list the sets. Now, there are a couple ways you can modify this notation. One, you can say something like A, B, dot, 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 E. You can use ellipses to represent some pattern that should be picked up easily by the reader, but you don't want to spend the time writing it out. So if, for whatever reason, the set is very long, what I might do is just write out a few elements in a certain pattern, then write dot, 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 and I can describe the set to you that way. Another way to do it, sometimes actually writing it down in a pattern is also very difficult. So you could do something like, just put something that represents the form of guys in your set, and put a bar, and then you just put a description. So you can say, it's a letter of the alphabet, or more specifically, X is one of the first 5 letters of the alphabet. This bar, you could also do a colon, but I think the bars are more common. X is the first step. You get what I'm saying? Yes, they're using what we learned already. Steps too much right now. So this thing here, this bar is read such that. So if I was reading this, I would say, oh, this is the set of all X such that X is one of the first 5 letters of the alphabet. So I can list everything, or if I can write down a pattern, I can use ellipses to show the continuation of some pattern, or if the pattern is really hard for me to write down, I can literally describe it in a phrase or with some other mathematical notation as is necessary. And this is called the roster method. You should also be aware that we can give sets names. We usually give them names by uppercase letters, but not always. But that's a typical convention. Now, what does it mean to be in a set? There is a symbol for this. More notation. This symbol here means is a member of. Or is an element in, or is a member in. While this symbol with a slash through it means not a member of. So for A above, I can say something like A is an element of the set A. I can also say that C is an element of the set A. I can say the number 3 is not in A. Right? I can make these phrases. So that backwards, E like that means is a member of. Slash through it to mean not a member of. I want to introduce any other notation at this moment. So I want to start talking about tuples. Maybe I'll just continue talking about sets. Now this symbol means is a subset of. While this thing means is a proper subset of. And what does it mean to be a subset? We say A is a subset of B and write A subset B if every element in A is also in B. everyone that's in here is contained in there, we call A a subset of B. If A is known to not be the same as B, remind me, I should tell you what equal means. Then we write a subset of B without the equal. So this means it's a proper subset, potentially they're equal. And what does it mean to be equal? Sets A and B are called equal we'll take the naive view of set theory where a set is determined precisely by its members. So they're equal if they have the same members. And we write A equals B in this case. Now, let's do some examples to make sure we actually understand this notation. So if I have A equals A, B, C, D, if I have B equals A, C, D, E, B, if I have C equals A, B, D, I have D equals 1, 2, 3. Then the following could be stated. Then, what's the relationship between A and B?
A is a subset of B.
No, it's even better than that. This is actually true technically speaking, but it's better than that.
A is a proper subset.
Is repetition.
Nope.
B isn't a subset.
They're exactly equal. Why are they the same? Because a set does not care about repetition. It also does not care about order. So the fact that the B shows up in the second position in here, but it shows up in the last position there, is irrelevant to a set. Sets are unordered, they don't require repetition. In fact, you wouldn't even write this down in the first place unless you enjoy writing things down. That won't make a difference. So sets do not, they ignore repetition, they ignore order. A and B are precisely the same thing as far as sets are concerned. Now, what is the relationship between A and C? It turns out you can say C is a subset of A. In fact, in this situation, since we can actually read all the members, I can know for sure that C is a proper subset of A. Either of those statements would be true. I can say that D is not a subset of A. Can I say that A is a subset of C? No, because subset means everything that's in this guy is also in that guy. There's an E in this guy, it's not in that guy. Therefore, it is not a subset of C. We'll do some more examples with sets pretty soon, but just to make sure, while we're going through the notation, let's make sure we kind of understand what we're writing down. What else do I want to define? The empty set. This guy deserves his own title, his own own heading, subheading. The set with no elements is called an empty set. The notation for the empty set is 0 with a slash through it, or you write the squiggly brackets, but you don't write anything inside it. Once you write that symbol in any set theoretical context, it will be assumed that you're talking about the empty set. The empty set is a very important set. First day of class, in my set theory class, we started with the empty set. We basically said, pretend there's nothing in the universe except an empty set. Let's build math with it. It took us 3 weeks to figure out how to add 1 plus 1. Oh yeah, now I understand what 1 plus 1 means. Yeah, now I really get it, yeah. And after that, it just got crazy. Every class was just crazier than the last one. But yeah, you started with the empty set, and it's just a set with no elements in it. Pretend in the beginning of the universe there was an empty bag. That was the start of set theory. How do we get math from this? Cardinality is another important thing. This is a measure of the size of a set. Now, if the set is finite, meaning it has a finite number of elements in there, then the cardinality is the number of elements in the set. There are such things as infinite sets, and not all infinite sets are created equal, believe it or not. Some infinities are larger than others. We're not worrying about those, though. We're only dealing with finite sets, things that you can count up to in a finite number, finite amount of time, as opposed to an infinite amount of time. So, the notation for this, so the cardinality of the set A write A in like absolute values. So, or you can write something like N of A is also very common. Those are the most common notations that I think. So, you write absolute values around a set, it means you're talking about the size of the set. So, for example, again, if your A is A, B, C, D, I can write that the absolute value of A is 5. That's the size of this set. Called the cardinality of the set. Tell you about definition. Two sets are called numerically. Sometimes this is this word is left out. Equivalent. Right. So there's a difference between being equal and being equivalent. When we say two sets are equivalent, two sets A and B are called equivalent if the size of A is equal to the size of B. So, for and we write sometimes we write this A and we write that thing here. A is equivalent to B. So we can write this or that, and it means that they are numerically equivalent. So I can say A equals A, B, C, D. B. I can say B equals 1, 2, 3, 4, 5. And A is not equal to B, but A is equivalent to B because they have the same number of things. So these are equivalent sets. There are going to be times when you care about a set of things, but it's going to be very hard for you to conceptualize it or visualize it or write it down. So what you do is you use something that you know is equivalent to that thing that you can handle a lot easier. And in terms of sizes, a lot of the times dealing with an equivalent set is just as good as dealing with the original one itself. Yeah.
You still ignore repetition kind of strategy.
Yeah, sets always ignore repetition. Always. That's a standard part of their definition. We don't always want to ignore repetition, but we would use an object that's not a set. We would use something else, which I'll tell you about soon. What else do I want to tell you? Equivalent sets, cardinalities. What about power sets? Let A be a set. Its power set. Okay, so we can call the power set of A is the set of all subsets of A. So you take a set, think of every possible subset that you can create from this thing, and take a set and collect those in it, and you created what you call a power set. The notation here is big P of A. We call this the power set of A, and the P is kind of fancy. So, let's do an example. Yes?
I don't understand. If repetition is ignored and all the subsets are just composed of elements of A, then how is the power set of A ever different from A?
Because A would be a set of elements, while the power set is a set of sets of that element.
Oh, okay.
Right, so they're not the same. I'm going to do an example right now. Let's say A is AB. What would the power set of A look like? Basically, the idea is you want to create another set of sets. So you're going to take sets here, and you're going to collect pieces of A in it, all possible pieces that you can dissect A into. Now, one possibility is for you to choose nothing. That is a subset. The empty set is in fact a subset of every set. Another possibility is for me to open a set and collect the element A in it, but not the element B. Another possibility is for me to open a set, collect the element B in it, but not the element A. Another possibility is for me to collect both elements in a set. And that is called the power set. Notice it is a set of sets. Right? So I have one set, and the members of that set are other sets. If the members represent all possible subsets of this guy, we call it a power set. So I want you to note here, for every A, the empty set is a subset of A, and A itself is a subset of A. And okay, let's you guys have some practice here. Suppose B equals 1, 2, 3. Find its power set. Suppose C equals the empty set. Find its power set. Suppose D equals the set that contains the empty set. Find its power set. So a set is just a collection of objects. The objects, in fact, could be sets themselves. That's going to be an actually important concept later on. So let's go. So I know that this is going to be a set of things. What are going to be things in that? The empty set is going to be one of them, meaning choose no one.
One.
No. The set containing one. They're very different.
The
What is
set
another
containing 1, 2.
Sure, the set containing 1 and 2. Yeah,
The set containing 2.
set containing 2.
Set containing
The set containing 3.
The set containing 2.
The set containing 2 and 3.
1 and 2.
The set containing 1 and 3. Coming in?
1, 2. The set containing
Set containing 1, 2, 3. Well, we're missing 3 and 2, right? Set containing 3 and 2? Right. Repeats are not. The order doesn't matter. So that's that. How many guys do we have here? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 total subsets of this set. What is the power set of this? So this is a set. Yeah, it's just itself because there's no one in there. The set containing the empty set is the power set of the empty set. What about the set containing the empty set? What is the power set of that set? Set containing the set.
Only 2 empty
The
sets?
set containing the set.
It would be the set containing,
The set.
well, the empty set is automatically a candidate. Anything else?
The set containing the empty set?
Well, the entire set itself, right? So the power set of that has 2 things in it. Question. What is the size of the power set if the size of A is n, some finite number? Do you see a pattern? Yeah.
And factorial.
Is it? So let's look here. The size of B is what?
That's
3. 3 factorial is?
6.
6. That would be 3 times 2 times 1, so it's not n factorial. Yeah?
Times 2.
Coming in?
N times 2.
N times 2 in this case would also be 6, right? Because n is 3 here. If I take 3 times 2, I would get 6. That's not good. Yeah.
Squared minus 1.
Square what minus 1?
Like square the size of the set minus 1.
Okay, so if I square that size, so if I square 3, I get 9, and minus 1, I get 8. Okay? Does that
No.
work here?
No. Who raised the n?
Because here the size of C is 0. The size of the power set of C is 1. Here the size of B is 3. The size of the power set of B is 8. Here the size of D is 1. The size of the power set of D is 2. Whatever formula you come up with has to match all of those. If you square it and subtract 1, it only actually matches that one. So, any other guesses? Yep,
Is it 2 to the n power?
it's 2 to the n power. That is the answer. The size of the power set of a finite set will always have 2 to the n things in it. The empty set has 0 things in it, its power set will have 2 to the 0. A set that has 1 thing in it, its power set will have 2 to the 1. A set that has 3 things in it, its power set will have 2 to the 3. Now we're going to talk about this as a counting principle in a little bit, but if you're wondering why this would be the case, one thing you can notice is that to create a power set, if you were like a machine and you had to describe to something how to create a power set, basically you can describe it in terms of choices. At every time, it is going to choose what element it wants to put in a subset versus not. So, the empty set means it made the choice no for everyone, right? This set means it made the choice yes here, but no here and here. This would mean it made the choice yes here, but no here and here. This would mean it made the choice yes here, but no here and here, and so on and so forth. So, because there are 3 elements in it, and you're choosing yes or no, you have 2 choices for every element, which means you would have 2 times 2 times 2 choices. You'll have 2 to the 3 choices. But we'll actually come back to that. We're actually getting a little bit ahead of ourselves here. But this is going to be the size of a power set. The size of a power set is always larger than the size of the set itself. In fact. What else do I want to talk about? Power sets are important. And this idea, like a set containing sets, is also pretty important for probability. Because in probability, a lot of things hinge on something called the sample space. And the sample space is in fact a set of sets. What else do I want to talk about? Do I want to talk about anything else? A tuple. We're going to define a new kind of object called a tuple. A tuple is an ordered collection. So you can almost think of it as a set where the order actually matters. It matters who comes first, who is second, who is third when you list these things. That allows and remembers repeats. The notation for a tuple is pretty much the same notation as we use for coordinates, actually. So, coordinate notation. That means I can call T a tuple, and it could look something like A, B, C, D, right? And I don't write squiggly brackets, I write round parentheses. Okay. Now, this is a tuple, in fact it's called a 4-tuple, or a quadruple. I can also talk about another thing, T, called A, B, C. This is a 3-tuple. Something else, so you don't mix these up. Or a triple, you can have K, equals AB. This is called a two-tuple or a double or an ordered pair. This is called an ordered triple here, etc. So you can have tuples. Now, the thing with tuples, as I mentioned, the order actually matters. Order matters for tuples. Meaning, if I have A, B, C, it is not the same as, say, B, A, C. A tuple would consider these two things different, because here the first position is A, here the first position is not A. It will consider these as different things. It also does not consider it the same if the A is repeated. In fact, this is a 3-tuple, while this is a 4-tuple. A tuple is kind of like a set. The difference is it has memory and it cares about order. So there are times when I want to represent a situation or an object or some set of facts, and I want to represent it in such a way that the order matters and that repeats are allowed without me erasing that information. So as an example here, we can do, say, if I were to represent the grades of a student in a class, I would not use a set, I would use a tuple. Why? Because a student can get the same grade on 2 different assignments. And moreover, if they get the same 2 grades, I don't want it to be erased. So I can put, like, in the first coordinate, I can put the grade for exam 1. In the second coordinate, I could put a grade for exam 2. In the third coordinate, I could put the grade for the final. And then it will be known to me that, oh, the first position is the first test grade, the second position is the second test grade, the third position is the final grade. So the student could get like a 95, and get a 95, and then get an 89. And I want to remember the order because it matters to me that the 95 is taken as exam 1, not as the final or something else. And I want to allow repeats because I don't want the fact that the student got a 95 2 times cause you to automatically erase the 95, right? So this is a tuple, it would be better for the test grade. Right? A set will be horrible for test grades. Right? So if I put this in a set that the student got a 95 and a 95 and then an 89, the set is going to say, forget the 95, why are you repeating that? It's going to think of this as 95 and 89. The set is also going to think of this as being exactly the same as that. And then I'm going to, which one's the final? Which one's the second test? Right? So I would not want to use a set to represent this kind of data. I would want to use a set that represents kinds of data where the order does not matter and repetitions are not allowed. Okay? And we'll get to it later, but this is actually the crux of solving a probability problem. A lot of the times you win or lose the battle in the very beginning. I give you some probability problem to figure out. Based on whether you think of it as a tuple or a set, will describe what you do for the rest of the problem. Once you initially imagine the wrong kind of thing, chances are you're going to get the wrong kind of answer. And most of the time when someone gets a probability problem wrong, this is kind of the problem. They're either thinking of order mattering when it doesn't, or repetitions being allowed when they're not, or vice versa, and they're very different. Sometimes you want to think in terms of sets, sometimes you want to think in terms of tuples. And more specifically for probability, you want to often think of as sets of sets or sets of tuples. Yeah.
Are tuples like lowercase letters all the time, or is that just
No, it's just convention. So sets are usually uppercase, tuples usually lowercase, but they can be whatever. So as long as you define something, you know what you're calling it, or the problem will define it for you. That's the important part. Okay. So there are 2 kinds of ways we can collect data, and it's going to be important depending on the situation. So if I'm collecting data on a race, for example, Like the shortest time wins. It matters who came in first, who came in second. If I am collecting sets based on poker hands, there's no inherent order, but repetition is not allowed. The situation is going to change based on what you want, and you should know whether to choose sets or tuples in order to set it up. And I'm going to talk about when to choose which soon. But for now, just know that there's something also called a tuple. Has anyone ever seen tuples before, like in this context? I mean, you've seen it as a coordinate, like an x and y coordinate, which is the same kind of thing actually. The first digit is always what's on the horizontal, the second digit was on the vertical, right? Everyone knows the first digit means something special compared to the second digit. And it was a tuple, right? You wouldn't want to represent an x-y coordinate as a set, because then who's the x and the y? And then if you're at the origin, well, what are you talking about? There's just, right? So you wouldn't want to represent coordinates on the 2D plane as a set. You'd represent it as a tuple. Because you want to allow order to matter, you want repeats to matter. Commonsets. I just want to reserve the right to use these at any time. We call n, this is the set of natural numbers. These are 1, 2, 3, 4, going on forever. Some sources include 0. I will not include 0, but boldface n might be different by a 0 being added in here. We also have what's called the integers. The z is for the German word Zahl, which means number. So that's where the z comes from. So this means 0, plus or minus 1, plus or minus 2, plus or minus 3, so on. All positive and negative whole numbers and 0. We also have the set q. These are called the set of rational numbers. Rational from the root word ratio, it's when we take a ratio of two integers and the denominator is not 0. Now, it's very hard to actually write down a list of all these guys that will capture the pattern for you, even though it just means a list of all fractions. But usually we represent it as a divided by b, such that a and b are members of the set z, and b is not equal to 0. The real numbers is also an important set. And this one is very, very complicated to actually describe, even though everyone knows it intuitively. Could say the set of all decimal expansions is one way to do it. Set of all the numbers on a number line, the completion of Q. Tons of ways to describe it. We also have C, which is called the complex numbers. It's everyone that looks like A plus IB, where A and B are real numbers, and I is the number -1. I'm pretty sure we're never going to have to worry about this set in this class. But if you see something like this, in fact, I've kind of used this before when we were solving systems of equations. And I mentioned that, oh, this has infinitely many solutions where z could be any real number. I said that. So, just in case you see that in the homework or anywhere. So, new definitions, I don't want to forget any. Now, the size of all these sets are infinity, right? But it turns out that some infinities are larger than others. It is a fact that you can prove, I'm not proving it in this class, but that the number of elements in here, whatever number means in this case, is actually the same as the number of elements in the integers, which at first glance seems to be really weird because it almost looks like that one has twice as many guys as that one. And turns out that's also the same as this number, the number of things, a set of all fractions. However, all of these guys are less than the size of R. There are more real numbers than all of them. R outweighs all of them by a lot. In fact, if you were to take R and throw away all the integers, throw away all the whole numbers, throw away all the fractions if you want, you would have the same number of things left over. It will not make a dent. It will be like nothing was taken away. So R is a lot bigger than the others, and C is the same size as R. You don't have to worry about why that is. Just know those as facts. It might come up. Yes.
What is C again? Like the
It's called the complex numbers. Basically, it's the set we invented to be able to solve equations like x squared plus 1 equals 0. We really wanted to be able to solve that, but we couldn't with the real numbers. Yes. So, we have a lot of definitions because we're playing around with sets. And probably even next class we'll continue with a few more definitions, but after that is out of the way, we'll start to do stuff with them. Let's talk about universal set. We don't consider sets in a vacuum. Every set is always thought of as being a subset of some other set. There's this mysterious big set in the background that contains everyone in that we want to consider. This larger set is called the universal set. Often denoted by a fancy uppercase U. So if I say, oh, there's a set A that's doing blah, you always imagine that in the background there is some giant universal set where this A lives in that set. There's it lives in some universe. Now the universe will vary on context, but just know there's always a bigger set in the background, no matter what set you're looking at. And this is called the universal set. The complement of a set. Let A be a set, let U be the universal set. The complement of A. If that wasn't here in my or whatever. The complement of A, or A complement, is the set of all elements in U that are not in A. So, example. U equals a set 1, 2, 3, 4, 5.
5.
A equals the set 1, 2, 5. Then, a complement. This one also has several notations. Sometimes it's write A with a C up top. It's probably the one I would use more often. It's also possible that they write with a C and an apostrophe. It's also possible that they write it with an A and a bar overhead. But they all mean the same thing. Different notations for complement. I really feel like that's an E. To be consistent. Okay. Anyway, what would be the complement here? It's going to be the set of all things that are in here, but at the same time they're not in there.
3, 4.
So the set containing 3 and 4 is in the complement of it. You can visualize this, and you can't always visualize sets, but you have a box, and you have all these numbers in there, like 1, and 2, and 4, and 3, and 5. And what you can do is you can put all these guys in a group, you can surround them, and you can label that guy A, while the box itself will be labeled U. This way of representing sets is called a Venn diagram. It's named after a guy with the last name Venn. I don't remember his first name, probably John, but this diagram is called a Venn with an uppercase V diagram. Okay, the box represents the universal set, and you can put sets inside this set, putting them in circles. Like here's a set A versus a set B, and you can move them around and do things with it that will represent the situation. And we'll actually start to play around with that a little bit next time. In fact, we'll stop there, but next time we'll start doing these stuff. So pass these around, and then I'll see you guys on Thursday. For the time.
Here.
Next time we'll have 2 more definitions, and we'll start to do some examples, including those that I just handed out.